This is review session number 3 following questions number 58 to 66 on the pretest. Taking a look at question number 58 is talking about kinetic molecular theory. And if you look at the definition for kinetic molecular theory, you see that all the particles are in random constant straight line motion. So the answer for number 58 would be 1. If you look at the other answers, number 2, that's the definition for a solid. Number 3, that's talking about a real gas, not ideal. And number 4, it just doesn't happen. In question number 59, it's talking about conditions where you have a real gas, so it's least likely to behave like an ideal. Therefore, you're talking about particles that are closer together. In order to get particles closer together, you got to squeeze them together, so usually you're going to have high pressure, and the temperature is also going to be low. So the answer for number 59 is 1. In question number 60, it's talking about the relationship between Kelvin temperature and volume. And we know that if the temperature increases, so will the volume. Both of them increase together. So the only one that graphically shows that is number 3, because both of them increase together. In question number 61, they're talking about which gas is not going to behave like an ideal gas. So they have the same temperature, they have the same pressure, so that has nothing to do with it. But in this case, we're going to look at which one is the largest. So the largest is least likely to be ideal. Though we're looking for the real gas. You look up all 4 of those on the periodic table: xenon, krypton, neon, and helium, and you find that xenon is the largest, therefore that's least likely to behave like an ideal. Now, if the question we're asking for the one that's most ideal, that would have been helium. So in this case, number 61 is 1. Number 4 is the answer for number 62, because we're talking about a real gas most like ideal. So most like ideal means we want to have the particles further away from each other. In order to get the particles further away from each other, we're looking for the highest temperature and the lowest pressure that we can have. So that combination would be number 4. And then in question number 63, we're looking at conditions that would have a 2-liter sample of oxygen, the same number of molecules, like Avogadro's hypothesis, as this 2-liter sample of nitrogen. And they do tell you that the conditions are STP, so they do tell you a temperature and pressure. So for nitrogen, your volume is 2 liters. The standard temperature is 0 Celsius, not Kelvin, it's 273 Kelvin, and the standard pressure is 1 atmosphere. So we have that information about nitrogen. Now for oxygen, we need to have the same information, the same conditions, in order to have the same number of molecules. So we have the 2 liters, so we need 0 Celsius or 273 Kelvin. And we need the standard pressure of 1 atmosphere. So the answer for number 63 is 2. In question number 64, we're looking at a gas sample that has certain conditions of volume, temperature, and pressure. You see you have 12 liters at 0 degrees Celsius and 0.5 atmospheres. You're trying to find the new volume, so you're trying to find V2. The pressure is now 1 atmosphere, but the temperature is held constant. And we said when you have the temperature constant, you can actually remove it from the equation. So let's take a look at what that looks like. Number 64. Okay. So if you look at this, we have the P1 V1 over T1, P2 V2 over T2. That's what we found from the reference table. But since the temperature is constant, we took out the T's. We have our givens of 0.5 atmospheres and 12 liters for the volume. We're trying to find V2. We set up the equation without the temperature values. We solve for V2 and you have 6 liters. Going back now to question number 65. In 65, you have standard temperature, pressure. Remember, those are actually numbers, so you have a temperature value of 273 Kelvin. You have a pressure of 1 atmosphere. You have a volume of 250 milliliters, but now this time the pressure is constant, so we can actually cross out pressure. Remember you said to change the volume to 500 milliliters, not 50 milliliters. And when we set up the equation, it looks something like this. Okay, where we have the pressure crossed out from the equation we got from table T. So we have a volume 1, 250. Temperature 1 is 273 from the STP that was given in the question. We have V2 is 500 milliliters, and we're solving for T2. If you cross multiply, you actually have your equation as set up as T2 times 250 equals 500 times 273. And you solve for T2, you have 546 Kelvin. And then for the last problem in this section is number 66. A gas that has a pressure of 120 kPa, volume of 50 milliliters. Temperature is 127 degrees Celsius. Remember, it can't be in Celsius, must convert to Kelvin. So you add 273 to that. They want to find out what the volume is, so you're looking for V2 if the pressure now changes to 60 kPa, and the final temperature is negative 73 degrees Celsius. Again, you cannot have Celsius, you have to convert that to Kelvin, so add 273 to that value also. This is what the problem is going to look like. Question number 66. Let's make that a little larger so you could see it better. There we go. So we have the equation P1 V1 over T1 equals P2 V2 over T2. Again, that is from table T. We have all of our givens set up like we normally would have. Make sure that you convert your temperatures from Celsius to Kelvin. Put all the numbers into the equation as you see done below that. And you're solving for V2. Therefore, you're going to be cross-multiplying, bring the 200 up to multiply it times the 120 times the 50, and then you're going to have the 60 come down, multiply to the 400, so 400 times the 60 on the bottom, and then you have 120 times 50 times 200 on the top. You're going to solve for V2, and V2 comes out to 50 milliliters, which is answer number 2.